Hey everyone, welcome back to another explainer. Today we're diving into a really intricate game of trade-offs, one that literally happens every single day in analytical labs around the world. We're talking about the art, and really the science, of optimizing chromatographic analysis. It's this crazy balancing act, right, where changing just one tiny variable can throw absolutely everything else out of whack. I absolutely love unpacking complex systems like this, so let's just get right into it.
Okay, so here's our roadmap for today. We'll kick things off at the quest for separation, navigate through the optimization challenge, and then we'll hit what's called the chromatographer's triangle. After that, we'll look at balancing time and resolution and wrap up with how software comes to the rescue.
Section 1, the quest for separation.
So before we even talk about optimizing a process, we really need to nail down why we're doing it in the first place. Think about this for a second. How do you measure the inseparable? Because analytical chromatography is inherently used for quantitative analysis, figuring out exactly how much of a substance is in a sample, it is absolutely crucial that we precisely measure the areas of the peaks. But if those chemical signals are overlapping, if your substances aren't fully separated, well, getting a precise measurement of those peak areas becomes basically impossible.
And that brings us to chromographic optimization. Simply put, it's the process of using all the resources your instrumentation has to offer. We're talking about simulating and modifying things like temperature, phases, and other physical parameters, all to achieve those perfectly separated substances, because that's how you get precise peak area measurements. But here's the kicker. To optimize effectively, you have to genuinely understand the chromatographic process. You can't just go in blindly twisting knobs and hoping for the best.
Moving right along to Section 2, the optimization challenge. Let's think about the sheer number of variables you have to juggle here. Take gas phase chromatography, for example. Separations can get so incredibly complex that it's often genuinely difficult to figure out if you should be turning the temperature up or down. You've got the choice of the column, its length, its diameter, the stationary phase, the phase ratio. All of these impact the separation. And to make it even more of a headache, they're all completely interconnected. Change the column length, and guess what? You probably have to rethink your temperature. It's a massive puzzle.
So, with all those dizzying variables, we have to keep our eyes on the prize. In the whole optimization process, resolution and dilution time are really your two most important dependent variables. The ultimate goal? To separate the components you actually care about in the absolute minimum amount of time. That's what it all boils down to.
Which leads us perfectly into Section 3, the chromatographer's triangle.
This constant push and pull creates a really fantastic visual metaphor, the chromatographer's triangle. You've got these three apexes: resolution, speed, and capacity. A truly optimized analytical separation uses the most efficient parameter, which is selectivity, to get as close to that resolution apex as humanly possible. You want that high resolution, for sure, but you are constantly fighting the gravitational pull of speed and capacity.
The source material actually frames this in a brilliantly dramatic way. It says, "The chromatographer is always a prisoner of a triangle, whose apexes correspond to resolution, speed, and capacity, three parameters that are in conflict." A prisoner of a triangle. I mean, it sounds intense, but it perfectly captures the constant negotiation chemists face every single time they run a sample.
Because let's face it, you simply can't have it all. It is a direct trade-off. High resolution almost always means you're going to suffer on speed. And if you really push for high speed, your resolution takes a hit. Keep in mind, chromatography is fundamentally a pretty slow type of analysis anyway. If you try to rush it, you're usually sacrificing the exact clarity you need to measure anything accurately. All right, Section 4, balancing time and resolution.
Let's step away from the abstract triangle and look at this in practice. These chromatographs perfectly illustrate the optimization of a mixture of aromatic hydrocarbons. Here in this specific liquid chromatography setup, they optimize the separation by successively tweaking the mobile phase, specifically a binary mixture of water and acetonitrile. And notice what happens as they dial in that resolution to get those beautiful, distinct peaks. The cycle time for the analysis goes way up. Getting that better separation literally just takes longer.
But there are some clever workarounds. Let's say you're in a situation where your resolution is already fantastic. Well, you can actually still optimize, but this time you do it to save yourself some precious time. You can just swap in a shorter column. This works because, mathematically speaking, resolution varies with the square root of the column length, so it's a neat little shortcut to claw back some speed without completely ruining your data. However, when we talk about speed, we have to be realistic. Minimum time isn't just how fast your substances elute.
you absolutely have to factor in the instrument recovery time. That's the time it takes for the whole system to reset, come back to its initial state, and actually be ready for the next run. You can never ignore the reset button.
Finally, Section 5, Software to the Rescue.
So what happens when human optimization hits a wall? When you've manually tweaked the temperature and swapped the columns until you're blue in the face? Well, when conventional methods aren't enough, and this happens a lot in liquid chromatography, where mobile phase composition is so critical, you turn to specialized computer software to help find that perfect composition. And if that still doesn't do the trick, that's when you bring out deconvolution software, or what's sometimes called fuzzy logic.
Fuzzy logic is basically the ultimate analytical hack. When you have two unresolved peaks that are stubbornly mashed together, the software steps in. Working under certain assumptions, like assuming the peaks are Gaussian, it can literally deconvolute the areas of those overlapping peaks into distinct, perfectly separate Gaussian components. Suddenly, those areas are super easy to measure. It just untangles the knot digitally. Which leaves us with a pretty fascinating question to ponder. If fuzzy logic and advanced software can untangle what is physically unresolvable, will advanced computing eventually just shatter the walls of the chromatographer's triangle entirely? Are we looking at a future where we are no longer prisoners of resolution, speed, and capacity? It's a seriously exciting frontier for analytical chemistry. Thanks for hanging out with me for this explainer, and keep questioning the data.